Hello, welcome to the section which talks about memory management in the OS. So to start with, let us see what is memory management and why is it needed. Then we will get into the discussion on what is paging and how is it implemented in an operating system. Now, so let us see what is the motivation for us to manage the memory. Now, which memory we are talking about? This is about the main memory, which is nothing but DRAM. Mostly we are saying, this is implemented using dynamic random access memory. Now we have our operating system which is or needs to run on this, okay, and our CPU which is running the operating system, and it accesses the main memory through one hardware unit called memory management unit. Now, what is the job of memory management unit? Whatever the addresses generated by the CPU by running a program into some addresses which refers or accesses the physical memory. Now, what is in is main memory is a physical memory, which is what is there in your laptop or a machine. 4 GB RAM or 8 GB RAM, what we talk about is actually referring to this main memory. The other name is main memory or physical memory, because we call it as physical memory because this is what is physically present in the system. Now, one more important thing to remember is any program, if it has to be executed by the CPU, that should be in this main memory. Now, we also have a hard disk which is of terabytes of space, which holds the image of OS, images of all our executable in this hard disk. Now, before we run any program, we bring it to the main memory and then run it. Now, who is doing it? It is the job of the OS with the help of the device driver, hard disk device driver, which helps the OS to bring the file into main memory. Now, you know that even the OS is residing in Windows directory or wherever the Linux is, that image is there on the hard disk or SSD, okay, solid state device. When the booting happens, it is brought into the main memory. Even the OS image is in the main memory. Now, let me say this is the address 0 to some maximum address 4 GB. What happens is some area is reserved for operating system, because OS needs to be there in the main memory because that needs to be executed. And as I told that any program to execute, it should be in main memory. That means the OS image also should be in the main memory. Now, can it be swapped out? Actually, the basic image, the core of the operating system should always be in the main memory, which should not be swapped out. When I say swapped out, means that image is copied into the hard disk to create some space for other programs. But OS is a must and it needs to be there in the system, and it occupies some part of the main memory. Now, let us assume that we have a 32-bit machine. Then we know that the maximum addresses could be 2 power 32, which corresponds to 4 GB of locations, 4 GB of bytes, 4 gigabytes. Now, how much is the area reserved for the operating system? Now, let us just take an example of Linux. Normally, what is happening is we have one constant which is page size, okay, which is actually deciding what will be the total area that is reserved for the operating system. Now, let me come to the OS. There is a memory called logical memory, okay, logical memory or a virtual memory. Let us not differentiate between these two, though within the operating system in Linux they mean something different as far as the OS image is concerned. We are not differentiating this when we talk about the user applications. Let us talk about OS. Now, OS also has its own logical memory, and normally it is given as this address 0x, this is C, 1000 and 1000. That means if you count each nibble is 4 bits, so it will be totally 32 bit. So this address is there within which our program's OS image is there. Now this is mapped to the lower part of the physical memory. Okay, and we decide about the space size, how much space we need. Normally it is, this is the space which is reserved for OS and which is directly mapped to this address. That means any address that generated by the OS is C1000 and 4 zeros followed by that is mapped to some address here in the physical memory. So let us not go into the details of how it is done internally. What I am trying to say is that OS needs to be there in the physical memory, and it does not use when OS is accessing its own code or data or its own stack, kernel stack. When I say OS, it's kernel. When it is accessing its own kernel code or data or the stack, it does not use the memory management unit, because OS to run, if we use MMU, if we need to use MMU, who will configure the MMU? Because it's like a chicken and egg problem. OS has to run without the help of MMU to start with, but it should be in the kernel mode, and the OS is the first code to be booting, and the CPU should be given the control of the OS to start with, and then it brings the other user applications later on. So right now what you need to carry it in your mind is that OS also has a logical memory addresses as far as Linux is concerned, and it has a direct mapping of some lower part of the physical memory which is there. Okay, now imagine OS is already booted and it is available in the main memory, some part of the main memory which is protected and user processes cannot access them or modify them. Okay, now the balance, if I have to say 3-4 GB of total physical memory, 3 GB is reserved for user processes. Okay, now before we go into the logical memory and then the CPU generating that logical memory addresses through MMU, it goes into physical memory, right? Now why do we need logical memory? Now let us just briefly talk about it. We need logical memory because every program can assume its own maximum space of 3 GB. Okay, let us assume in the Linux case, I told you that 3 GB of user space is there. Let us assume that we cannot go beyond it and we are only talking about 32-bit machines. Okay, 64-bit machine has again unlimited space, not unlimited to be precise, but much more than 3 GB. But for our discussion, let us assume that 3 GB of virtual address space is available from the Linux support perspective on a 32-bit machine. Now, suppose if I write a program, process P1, assume that it has 3 GB of space. Now, I may have another executable, right, which is process P2, which also assume that it has 3 GB of space, because in Linux, in a 32-bit machine, user processors are given a virtual space of 3 GB. Virtual space, not the physical memory. Now, suppose for our discussion, let us assume that main memory has some space. Let us not take the same 3 GB of space. Let me say that only 1 GB of RAM is there. Now, this 1 GB of physical memory is shared between these two processes. Okay, but they assume that each one of them is having 3 GB of space. Now, what is the job of the OS? Which is giving an impression to both the processes that it has 3 GB of space for it. But available space is 1 GB for our discussion I am taking, because maybe another 1 GB is consumed by OS. We have only this much of space, and this is also shared between process P1 and P2. It's not that only two processes are there. There can be n number of processes, user processes. I am talking about user process. Now each one of them has a freedom to think that they have 3 GB of space. Now when the CPU is executing this program, what is the job of the OS while configuring the MMU? MMU is a hardware unit which is translating every logical address or a virtual address generated by the program, because once the process thinks that it has 3 GB of space, linker and the loader and the other modules could have distributed this into multiple areas. Maybe it would have reserved some space for code, some for data, and maybe for stack and heap some space which is maybe going towards each other. So this 3 GB, it has divided itself into some area, and similarly the other processes also could have done it, because imagine every process is getting compiled and linker is building all the executable and then generating a final executable. Now that final executable, assume that this is the logical space it has, and assume all the both the processes it has 3 GB of space it wants to use. But in real life, you have only 1 GB of space, and that is also shared between these two processes. So what happens is, because of the locality of reference, which we already know, locality of reference, that any point in time, a program is always working on some part of the code which is accessing some part of the data. Maybe it is using some another area of stack while the function call is being called. So what is needed at the time is, suppose if you buy a whole book, you are not going to read the whole book at the same time. You are going to read page by page. So when you are having a ebook reader or something, it displays you page by page, and then you may suddenly decide to say that I want to go to the page 200 to refer something, or index page to know what is the expansion of some acronyms. Then what happens, your focus goes to that particular page, and that page is brought onto the front page, right, on the screen. Similarly, whenever the program is executing and it wants to access some part of the area, code or data, and the stack is growing because you are keep calling functions, it is provided to you whatever is needed at that moment. So what you need is not the entire book, you need a one page. Similarly here, the memory or what, it may need some part of the code, some part of the data, but it's not the entire space that the program assumes it has. But what happens in real life is, whenever the code execution happens and it flows through the dump part of the code, that whatever is of interest is brought into the main memory. Who is doing it? The MMU is doing it. How does it do? OS knows what is the area needed and which part of the code or data is being accessed, and that is brought into the physical memory. Now, to do that, the CPU or sorry, the OS needs to maintain some information about each of the processes, because it needs to map the logical address generated by the program. When I have a pointer or a function pointer or a data pointer or a pointer to a variable, they all refer to the logical memory space, which is the program assumes that it is accessing it, and it is converted into physical address space based on where that particular part of the data or code is brought into the main memory by the OS. So OS knows which part of the code or data from the hard disk, maybe I'll assume that hard disk is there, both the P1 and P2 are residing here in terms of memory image, and they are brought into the main memory as and when it is needed. So to do the translation, there's called page table is there, which we will talk about it later. Now this is the general understanding of what a process assumes and how does the OS gives an impression that whatever the OS process needs is already available. Now only caveat here is that the processes need to wait if a particular page is not available on the main memory. It needs to be page fault happens and then it is brought into the main memory as and when the program needs it. Now, another important thing that you need to remember, the main memory, the memory management unit, what gives you other features is that, and a virtual space which need not be equal to the physical memory you have. Okay, it can be much larger than what physical memory you have. So you are still able to run your program because of whatever I mentioned, the needed one things are brought. Now other thing is, suppose if you are declaring an array, my array, okay, of 10,000 elements. Now this is imagine that integer is 4 bytes assuming a 32-bit machine, then you will have 40,000 bytes needed to keep this or have an array. Suppose imagine that it is a static variable, a global static variable. That means the data area is so big. This array of 0 will be here and array of 999 will be here. Now, when you are having a array and then you are for loop and then you are accessing this array by indexing it, you are only going to access maybe from starting from 0, or maybe you may start in between, but you are going to access it in sequence. So you are not going to look at the entire array at the same time. Anyway, you cannot do it. You are going to update one element by element. So whatever is needed is brought into the main memory. And suppose if you modified something, it need to be and then if it is the particular page is removed and then you are bringing something else, then it should be saved. That I will talk about it soon. So if suppose your array is like this, in that case, the you can imagine the address of this array 0th element compared to maybe element of 1, element 2. You can see that this address will be lower than the address here because it is in the increasing order. It needs to be contiguous space. So that contiguous space of memory, what is needed for an array, is supported on the logical memory part. Logical memory, if you have taken the address of my array, okay, of 10, and then I take the address of my array of maybe 20. If I compare, the address of 20 will be more than 10 and the difference will be exactly 40 bytes because each element is going to be occupying 4 bytes and it's going to be giving you a difference of 40 bytes. But in reality, that locations of actual memory addresses of these variables, these elements need not be contiguous. Though, if suppose if I am having only for argument's sake only 100 elements of this array is there in the physical memory, they will all be in contiguous space. I am not saying that they will be swapped, but another part of the same array, which is maybe 100, first 100 element, then second 100 element, maybe up to 200, from 100 to 200, need not be in the same contiguous space. They can be, these addresses can be lower than this address. Okay, that means this contiguous space that you see in a logical memory in an array need not be contiguous in the physical memory, and all these 10,000 elements need not be present in the main memory also, and some part of it may be there, some may not be there, and whatever is there in the main memory need not be contiguous. So that is also taken care of by the memory management unit. Okay, so these are all the basic features. Now let me talk about one more thing that memory management unit supports. Now I may have a const int, okay, array of 10. Suppose I have a const array, that means I am already initializing it with some value, but I don't want that to be modified by the program at any point. Then wherever this array is there in the memory, though remember we are bringing it to a DRAM memory which is a read writable, but actually for some part of the execution or some part of the memory, while this array is residing in the main memory, this memory should behave like a read-only memory. You should not be allowed to write into this. But initially, to bring this value, OS is going to write this contents into this area. After that, it's going to say that, oh, it's only read-only when the program runs. So what OS does with the memory is different from what the program can do. Program, what it can do is decided based on the program control accesses that user has thought about. So he has declared this as a const, then this array is brought into the main memory by writing the content into it, whatever the user has initialized with, and later on it is going to be kept read only. So these read only access, or maybe some locations like stack where you have local variables or parameters coming in going out, they are all read writable. So that is also should be supported, read permission or read write permission, or maybe you may have a code which is residing in the main memory that should be read and executable, RX. So you should be able to read the up code, and then you should be a executable part of code, because when I say a part of the area which is a read and executable permission it has, that means that program counter is referring to that. Okay, program counter will always be pointing at the location where actual code is residing in the main memory. Remember again, this is also a RAM. Now it behaves like a read and executable area. And some part of the stack could be read writable. Okay, that's a data area. And the non-constant may be there where you might have declared some global variables which are not constant. Then it should also be read writable. So basically, we have contiguous space, we have larger memory space which is given to with a limited physical memory we have, and multiple processes can be sharing the same main memory without they each other getting into them and corrupting them. And then OS is also residing along with it, but still the user processes cannot do anything with the OS. So these are all the things which is done by the memory management unit with the help of the OS. Now read, write and executable permission which is there for the data area is what is also supported by the memory management unit. So this will give you an overview of what is the purpose of memory management unit, what it does. Now we will go into the details of how is it done by going through the slides. Okay. Now the paging is one mechanism which is used for performing this memory management, implementing the memory management. Paging is one way of doing it. Now, what is paging? We will do that. Before that, we had talked about fixed and dynamic partition. That means the main memory, whatever is there, is divided into fixed partitions, or it is divided into some variable sizes. Okay. Now, if I have the requirement of a particular process P1, P2, I have to make sure that it maps to one of this area, and it should be, if it is not possible to fit into that, then I will not be able to run the program. That means I have a problem that these are all, I need to make sure that the processes of different sizes are supported in the main memory. Now, if I divide it with a dynamic partition, that means sizes of different sizes, then if I partition the main memory into variable sizes, then I need to make sure that the highest size that process needs to be allocated here. Now, what if the set of processes which are to be run in the system is needing only smaller sizes? Then you may have to run them in this larger area by wasting lot of internal memory, which is called internal fragmentation. That means you are wasting the space inside the partitions that you have created. Now, other way of doing it is I fix it and then I have fixed partition. That means all my processes needs to be of that size. So I am not allowed to divide this existing process area into multiple fixed partitions. I always map one to one with a partition. So that's a very limited primitive implementation of memory management unit, which is not in practice, and we are just talking about it only for a academic purpose, that this is how the memory management evolved over the time. So internal fragmentation and equal size chunks that are relatively small, then each process is also divided into small fixed size chunks and same size with the same size. Then the chunks of the process known as pages could be assigned to any available chunks of memory known as frames. Now we will soon see that this method is of the wasted space in memory for each process is due to internal fragmentation of any last page of the thing. Okay. Now when I say that I have a process with equal number of spaces, then I will take one of the pages and map it to the physical memory fixed size. Now if I do that, only the last page, which may not be using the full page size, only that particular internal fragmentation will be there. The rest of it will be paging will be done. So what I am saying is, if I make it into a equal partition of pages, then this exact wastage will be only the last piece of memory. Now let me give an example. Now suppose if I have this kind of a requirement from the process perspective, I map it to a 2 kilobyte pages. What I am saying is, we have pages on this side, on the logical memory side, and then we have frames. We call this on the physical memory side, we call it as frame. Now page size is equal to frame size. Okay, so that needs to be taken care of. And then one more thing you need to remember is, it should be 2 to the power of something. Okay, you cannot have an arbitrary size of 236 of page size. Page size cannot be some arbitrary number, it should be in powers of 2, and page size should be equal to frame size. That means physical memory side we call it as a frame size, which maps a page into a frame. Okay, this is only for academic purpose, that you know what you are referring to, whether you are talking about a page which is within the physical memory, or are you talking about the page which is part of the logical memory space of the program. Okay, so now how many is, suppose if I am dividing this into 2 kilobyte of pages, then how many page frames are needed? So this is divided into 2 and 1. This can be exactly divided into 2 and 2, and this has 3 divisions. Okay, so this is one page, 1 1 3 4 5. Now this has to be mapped to 2, and this is one more. So we have this, and then we have two of them here. Okay, so this is one. So totally we have 7 frames we'll be needing it, because even if there is a requirement of 1 kilobyte, we have to give a page of 2 kilobyte, okay, or a frame of 2 kilobyte in the physical memory. So we will be using only 1 kilobyte in there. This is the wastage. This is the internal fragmentation, and the maximum weightage here, wastage is only 1 kilobyte of area. Okay, so I hope this is clear to you. Now, when will there be wastage of space when it gets mapped to physical memory page frame? Yes. How much is it? It's 1 kilobyte of space. Okay, and wastage space is 1 kilobyte. Now, data is, there is no wastage. We use entire thing is mapped to them properly. Now, what type of fragmentation is this? The wastage is internal fragmentation. How much are total wastage? 1 kilobyte of per code area. Should the process segments be aligned with the page boundaries? Process segments, whatever segments I am talking about, they should be aligned with the two memory. When I say that it should be aligned with the frame memory memory addresses, you cannot arbitrarily start the page on any address. It should be the powers of 2, and it should aligned with the memory. It is 0 to 2 kilobyte, then 2 kilobyte to 4 kilobyte, like this. You cannot have from, maybe I leave some 10 bytes and then start from here. No, it's not possible. You should be powers of 2, and it should be aligned with the addresses. Okay, so now let me take an example of main memory. We have 15 frames here. So I told you that on the main memory, the each page is called as a frame. Now we are moving some processes. Process, this is using 8 frames. Okay, and sorry, 4, and then this is using 3 of them, and other 3 processes are, another process needs 3. So this is how it has been moved. Okay, we are not showing the OS image here, we are only talking about the user area. Now suppose another process D has to be brought, which is needing 5 page frames. Can it be brought here? No. I see, one more thing I tell you. We initially we bring a resident set, okay, which is resident set nothing but what are the things you need, okay, set for a process to start running, and then later on I may bring one page after the other page. So initially it needs all the 5 page frames to be available on the main memory to start executing. Why? Because there should be some code, there should be data, and then there should be some stack area and heap area also may be required for a process to be running on the system. So we need all 5. Now how is it possible to do that? We cannot do it now because we have only 4 frames available. We need to move it out. That's what I said, that we have to clear some area by moving into hard disk. Where do you move? You move it to hard disk, so that whatever changes are done is also copied here, so that when it comes back, this process can continue running from where it left off. Right now, if I am moving in some D process D, I am moving out some other process. I can choose anything, but imagine that we are taking the OS is deciding based on some algorithm and decides to move out something from here. Okay, it has decided to move maybe B out of it, and then it is going to bring in D. Now you see a difference between what we have seen in the earlier stages of fixed size, and there is no method of paging mechanism. Now here we have a paging mechanism which allows you to have the pages of a virtual memory. The virtual memory pages are on the logical side they are all contiguous, but here they need not be contiguous and they need not be even in this order. I can keep D3 here and D0 here, no harm. As long as I map the D0 here to this location, no issues. As long as I map D3 to this location, no issues. It need not be contiguous, but within the page, yes, they need to be within the contiguous area of 4 kilobyte or 2 kilobyte, whatever the page size we are talking about. So this is the flexibility that I talked about. The paging mechanism gives you. So what we are trying to do is the logical memory is divided into pages of some size, and it cannot be too small or it can't be too big. Okay, when I say too big or too small, we'll come to that later. Now assume that either 4 kilobyte or 2 kilobyte or 8 kilobyte may be a reasonable size for a page. Then we divide the logical memory into that area, and then we have the same kind of frame size on the physical memory, and the memory management unit with the help of the OS maps them to the one of the available areas in the physical memory. Okay, so this mapping is done by the logic. No, this is the process area. I have 4 pages here and I call them as page numbers. Okay, and then they are mapped to some frame. This can be called as PFN in Linux terms, page frame number or frame number. Okay, now this page 0 is residing in the frame number 1, page 1 is residing in page number 4. Now the mapping of is done here. Okay, the 0 is coming here and mapped to 1. So whenever I access the page 0, any of the addresses within this, okay, it will be mapped to any of the addresses within that. So that transition happens. Okay, translation, not even transition, translation happens. The address is translated and brought here. Okay, I will come up with the great example and show you how exactly this translation happens, so that you understand how that address generated by the CPU, which are the instructions, maybe LDR or STR. If you are familiar with ARM instructions, these instructions are going to have some addresses stored here, and this address is the logical address, which is nothing but whatever pointer address you see on your program. If you are printing a percentage %p and a address of a variable, what you see as a logical memory address is what is generated by the CPU, which finally gets converted into some physical memory based on where it is residing, and memory is being accessed using that address, not with the address which is generated by the CPU. So that has to be kept in mind, and these are the ways the translation happens. We will talk about how it exactly happens in the next lecture. Now, right now, imagine that suppose I assume that 4 kilobyte of page size is there. Now, assume that page 3 of a process occupies only top 3 page. Suppose it only uses top 3 kilobyte, then actual size of the process is very simple. You 3 into 4, 12 plus 1, 12 plus 3, 15 kilobyte. And what is the type of fragmentation here? Internal fragmentation. And how much of wastage? 1 kilobyte again. What is the total size of the main memory here? I told you that page size is same as frame size. So this size is also 4 kilobyte. Okay. If I give page size, you can imagine that frame size is also same. It needs to be same. So now if what is the size of the main memory? This is what is shown. That means there are 8 page frames are there. 8 into 4. Okay. So 32 kilobyte is size of the physical memory. Now where is the page table located? It is located as a part of the MMU, inside the MMU. Okay, MMU is also within the CPU's core, and addresses are accessed, and then when the address comes out of the core of the CPU, MMU translates it and generates a physical address. Now, is virtual address supported here? Of course it is, because I am talking about MMU and page table and the frame number and page number. Of course you have to say yes. Okay, so why is it a single relocation register? Not enough. We talked about that when you don't have a paging mechanism. In that case, what happens is any address can be given an offset and you can access it with respect to that. That means whatever the logical address, you add some fixed offset. Okay, then the physical addresses will be accessed. If that is the case, you need to make sure that the processes are laid out on the main memory on a contiguous space only. I cannot do it this way, or I can't even swap random order, because they need to be whatever I see in the logical side. I told that this can be contiguous and it can be contiguous, that will be contiguous, but when it is converted using memory management unit with the paging mechanism, it need not be contiguous. Whereas if you are saying I'm using only one relocation register per process also, it's not enough for you to implement this kind of a flexibility there. So that's very obvious. And if you read through that, page table gives you freedom to switch or translate each page specifically into some other location in the main memory. Okay, whereas in process D they are not in contiguous space, a simple relocation register will not do the job. So that's very obvious, because if if I assume that one relocation register is there, I would have given the offset of this much to access D0. But when I go to D3, I will not be accessing this area. I will be accessing C0 area, assuming that this is D3 for my process, which is wrong. So single relocation register will not be enough. Okay, so page table of processes. Now suppose I have a page table for this, because this is a page table mechanism. Can you imagine of coming up with the entries of each page table for every process? But remember the one thing, that OS is maintaining a page table for every process, and it is mapped based on the current locations of those pages of a process, where exactly they are in the main memory. Now all the pages of process A is there, and they are all located in the same way. It's direct mapping, I would say. So zeroth page frame, zero page number is mapped to zeroth frame number. Okay, it happens to be like that. Need not be always true. Now what happens to the process D and C? Now look at the process D. It's not in the contiguous space. So but the page numbers will be contiguous. You can see that page numbers are contiguous, but frame numbers need not be, based on whatever it is mapped to. That is what is given here. So page table is maintained at process level, and it maps to the current locations of each page in the frame. Okay, and you know that page size is same as frame size, and it is to the power of 2, which we'll talk about it in the next lecture. Now what about process C? It is there available on the main memory, so I can show it. But process B is currently not on the main memory. But I remember that we know that it is actually was there in this location, right? So it was having B0, B1 and B2. That means the frame, assuming that page numbers are only this much and it doesn't need anything more, then right now it is left invalid, or no entry is there, because it is not present in the currently in the main memory. Okay, that's what a page table roughly looks like, based on where exactly the pages of a particular process are residing in the main memory. If they are not residing, then there won't be any entry for that particular page on the page table of that particular process. So it should maintain a free list. Okay, what all the frames are free? Okay, 13 and 14, so that when the next process comes, maybe it needs only 2 pages of its logical memory size, then that can be mapped into these 2 frames which are available freely. They need not be contiguous, but it happens to be contiguous space here. So OS maintains a page table for each process. Page table shows the frame location for each page of the page process. Within the program, each logical address consists of a page number and an offset. Now what is this offset I am talking about? When I am saying that 4 kilobyte of space for a page, 4 kilobyte occupies how much of address space? You have to see address is within this page, 4 kilobyte of space is there. Now 1 kilobyte is nothing but 1024, which is 2 to the power 10. So it will be needing, if I need to access 0 location to 1024, 23, sorry, because totally it is 1024, but it is 0 to 1023 is the address. Now 2 to the power 10 means 10 bits are there, B0 to B9. All of them 0 refers to this location of byte. I am talking about the byte array. And then all ones of this address B0 to B9 refers to the last location 1023. If you look at this value, which is all ones, 10 bits, if you have all ones, which will be 1023 in terms of decimal number. So if the 1 kilobyte is 10 bits, then 4 kilobyte you need to have 2 more bits, because one is, suppose if I have 4 kilobits are there, and within this 1 kilobyte, okay, we need 10 bits, okay, B9 to B0. Now if I have 2 more bits, suppose B10, B11, then what will happen? This 10 bits will take me, this is 0, it will take me from all zeros to all 1. Then if I increase it to 1 more, all zeros to all 1 will take me to next 1 kilobyte. Then I will have 1 0 1 0, then 1 1 1 1. So what I am saying is, for every 1 kilobyte I need to have some change in this higher order bits. So this higher order bits refers to the page number, okay, and the lower order 10 bits based on the size of the element, it will be offset. Now when I say it is a 4 kilobyte page, then I will have 12 bits here, which is referring to offset within the 4 kilobyte, because I cover everything. Okay, this including these 2 bits, I am going to consider it as a offset. And then if I have too many 4 kilobyte, then I will add some more. Suppose only two 4 kilobytes are there, then if I have to add one more bit here, which is this is B0 to B11, B12 will be 0 for this particular 4 kilobyte page, and then B12 bit will be 1 for next 4 kilobyte of space. This is what you have to understand, that how the addresses keep changing, and the offset is the lower part and the page number or the frame number is the higher part of the address. So within the program, each logical address consists of a page number and an offset. Recall that in the case of simple partition, the logical address is the location of the word relative to the beginning of the program. Okay, in a normal relative relocation register, it is the entire program is mapped to one location and the entire program is assumed to be contiguous in the physical memory also, which is not the case with the page number paging mechanism, because we can actually map page wise. We need to make sure that they are in the logical contiguous address, but each after one page frame or page boundaries, you can have it in any order there you want. With the paging, the logical to physical address translation is still done by the processor and MMU. Presented with the the MMU is presented with the logical address, page number and offset. The processor uses it and converts it into a frame number and offset. So what happens is, on the logical side, page number and the offset is there. Offset is not modified, only the page number is modified to another frame number. So your page moves to or map to some other part of the frame. So this brings to the end of this discussion on how paging mechanism helps you in achieving the goal of memory management. We will go into the implementation and see some more examples in the coming lecture. Bye bye.